Okay, so in this video I want to talk about the MOSFET transistor. And the first thing is, what does MOSFET stand for? MOSFET is an acronym for metal oxide semiconductor field effect transistor. So a MOSFET works in the following way. It uses a layer of silicon dioxide in between a piece of silicon and a piece of metal, and it creates a channel. As you apply a voltage to the metal gate, it creates a channel on the piece of silicon, and depending on how thick the channel is, the more current can flow into the piece of silicon. Now let me draw a MOSFET transistor here for you. So it's a larger piece of silicon here, and we call this the P plus type, and inside this larger piece there are two smaller pieces here, or wells, which are called N plus type. And this is, so the N type, we have N type silicon and P type silicon. So the well is made of the larger well is made of P plus, and the smaller two wells are made of N plus type. Now on top of this we have a thin piece of silicon dioxide, and this is the oxide layer, and on top of that we have a metal layer. Now sometimes this can also be made of polysilicon, polycrystalline silicon, so polycrystalline silicon. And nowadays this is usually made of polycrystalline silicon. Now how does this work? So we call this here the drain. This end is called the drain, this is called the source, and this is called the gate. Now let's ground the source. For this type, the source is usually grounded, and the drain will set that as a voltage V, usually 5 volts. It can be much less. And so this is also called the N-type N-channel, the N-channel MOSFET. There's also the P-channel MOSFET. We'll talk about the N-channel MOSFET here just for simplification, but the principle is basically the same. So what happens? What happens is, if you apply a voltage between the gate and the source, so if you apply a voltage between these 2 points here, then what happens? You apply a positive voltage on here, and the P-type silicon, it has less electrons available than the N-type silicon. Now the N-type silicon has an excess of electrons, so if you apply a positive voltage here, some electrons are going to move from here into here, from the N-type into the P-type, and that's going to create a small channel here, and this is going to convert this area here, this little channel, into N plus type, because we are drawing more electrons into this area here. And also, okay, let's see. So we create this channel, and now if we have this channel, now current can flow in here in this channel here, because now we have electrons available. And so if we apply now a voltage between the drain here, between here and the source, if we apply a voltage between these 2 points, then basically a current can flow on this channel here. And so that's basically how the MOSFET works. The amount of voltage you apply between the drain and the source is going to dictate how much current will be able to flow in the channel here. So okay, so let me draw the symbol, the schematic symbol for the MOSFET. Now there are many types of symbols. I'll draw a simple symbol for the N-type MOSFET, the N-channel MOSFET. So this is the drain, this is the source, and this is the gate. Here we have the voltage V. Here we have ground. And between the gate and the source, we apply another voltage. Let's call that voltage small v. So this is the schematic symbol for the MOSFET. So we apply a voltage between the gate and the source here, and after that then a current can flow from here into here. Now, how does this work? What law dictates how much current is going to flow in the transistor? Now, the first thing is the transistor will only be active if the voltage between the gate and the source, which we call VGS, is greater than a voltage VT, which we call the threshold voltage. Now let's take in this case the threshold voltage to be equal to 1 volt. And so if the voltage VGS is greater than 1 volt, then current flows. Then current can flow between drain and source. So this is the first requirement. If VGS is less than the threshold voltage, then no currents can flow because the channel will be really small. Excuse me. And so very little currents can flow between the drain and the source if VGS is less than V threshold. So the first requirement is VGS has to be greater than V threshold. If that's the case, then there is an equation that governs how much current is going to flow from the drain to the source. We call this current IDS, I drain source, and IDS is going to be given by a constant K times the following expression: VGS minus V threshold times VDS, which is the voltage between the drain and the source here. From that we subtract VDS squared over 2. And so this is the expression for the current in terms of the voltage VGS and VDS. For this equation to hold, again VGS has to be greater than V threshold. Now K is a constant which depends on the manufacturer of the transistor. So each transistor has a certain constant K, and the constant K can be written in terms of the electron mobility, UN, times the capacitance of the oxide layer, times the width of the transistor divided by the length of the transistor. And this is dependent on the manufacturer again. Let's not worry about these constants for now, I'm just giving them for completion. Let's just take them to be K right now. Okay, so the second thing is we can graph this this relationship. So let's create an axis here, and let's call this VDS, which is the voltage between the drain and the source, and this is IDS. Now, okay, so now the way this looks is there is one curve for each VGS you apply. So let's draw the first one here. So there's going to be something like this, more or less linear here, and then it starts to drift and curve and then goes on like this. This is for a certain VGS voltage you apply. Then there is another one here that will go like this. There is another one here that will go like this, and there is another one here which will go like this. As you can see, there's a different one for each VGS, and there's also one at the bottom here which is for VGS is less than the threshold voltage. So for example, this can be for a VGS minus V threshold is equal to 1. This is for VGS minus V threshold is equal to 2. VGS minus V threshold is equal to 3, and so on. And of course this also means that VGS is equal to V threshold plus 3, and so on. VGS is equal to V threshold plus 2. So the first thing to notice is that for each VGS you get a certain curve, and the curve starts off more or less linear, and then it curves off, and then there's going to be a point here. For each curve there's going to be a point. Let me draw this better. There's going to be a point here where the curve here becomes linear. This is called the saturation region. Again, this is also saturation, and saturation. And I'm going to draw a curve here which intercepts the point where the transistor becomes saturated, and this is a quadratic equation. It's not a coincidence that it looks like a quadratic equation. If I can draw a quadratic equation well here, this is a quadratic equation here, and wherever the quadratic equation intercepts this is where the transistor becomes saturated, and this is where this becomes linear. Now, as you can see, this is not a horizontal line like this. It has a slope. This slope is usually called lambda, and we can include this slope in the term here, which is 1 plus lambda times VDS. This is a linear equation here, multiplying this other equation. When the transistor becomes saturated, then IDS is going to be equal to a constant K times some other constant, let's say P, times 1 plus lambda times VDS. And as you can see here, this is just a linear equation, and this is going to be equal to 0. VDS is equal to 0 for VDS is equal to minus 1 over lambda. So that's going to be somewhere here. Let me draw this axis a little bit better here. So there's going to be a point here where this intercepts, and this is minus 1 over lambda. Let's not worry about this for now. I'm just adding it for completion. We'll talk about the more important aspects of the MOSFET for now. So as you can see, the MOSFET has two regions, where the first one is this area here to the left of this quadratic here parabola, and there is also this region here which is called the saturation region. This is also called the triode region, and this is called the saturation region. Okay, and now when does the transistor become saturated? There is a condition for this, and this is the first condition is that VGS has to be greater than V threshold, and the second condition is that VDS has to be greater than or equal than VGS minus V threshold. So if VDS, which remember is the voltage you apply between the drain and the source here, this is VDS, if this is greater than or equal to VGS minus V threshold, then the transistor is in the saturation region. This is G. And so we can determine the current that flows here, IDS, when the transistor is saturated. So we go back to our equation. IDS is equal to K times VGS minus V threshold times VDS minus VDS squared over 2. And when VDS is equal to, at this point when it becomes equal to VGS minus V threshold, this is where the transistor becomes saturated. So we can substitute this into this equation to get the current, the saturation current. So IDS is equal to K times VGS minus V threshold times, now VDS will be equal to VGS minus V threshold, so we write it here, VGS minus V threshold minus VGS minus V threshold squared over 2, and so this is equal to K times, now this is VGS squared, is VGS minus V threshold squared minus half of that, simply equal to this over 2, which can be written simpler as K over 2 times VGS minus V threshold squared. So this is equal to IDS, which is equal to the saturation current. Okay, so as you can see here, the current will depend only on VGS. And let's go back here. So this is the point where VDS here is equal to VGS minus V threshold. And so this is going to be, if here we have VGS minus V threshold is equal to 4, for example, then this is equal to VGS minus V threshold, this is also going to be equal to 4. Now there's one of these for each of these curves here. For this one, VGS minus V threshold is equal to 3. We go back here, this is 3, this is 2, this is 1, another one for 0 here. So now you can understand why I drew this quadratic equation here. This is precisely equal to this expression here, this one here, and we can substitute for VDS here, so you get IDS is equal to K over 2 times VDS squared, because remember VGS minus V threshold is equal to VDS at the point of saturation. So this is the quadratic equation that I have sketched here. You see? So this is equal to K over 2 times VDS squared. So this parabola here tells you where each of the curves here becomes saturated. So there's going to be an infinite number of these. There's another one here, there's another one here, and they all become saturated when they intersect this curve here. Okay, so this is basically how the MOSFET works, and this is one of the simplest models for the MOSFET. And in the next videos I'm going to talk about more in-depth aspects of the MOSFET. And so that's it for now, and thank you very much for watching.